Welcome back. In the last video, we built a multilayer perceptron, and it's powerful, flexible, and ready to learn. But here's the trap. Neural networks are often too good at learning. They can easily become like a student who just memorizes every practice exam word for word, only to completely fail the actual test. Today, we are talking about why deep learning models fail in the real world and the modern optimization tricks we use to keep them sharp, stable, and accurate. So, when training a model, we care about two distinct metrics, training error and generalization error. Training error is how well the model performs on the data it sees during practice, right? The data is trained on. Generalization error is how well it performs on brand new, unseen data. Model capacity refers to how complex of a function your network can learn. If your capacity is too slow, you underfit, which means you can't capture the signal, you can't really learn. But if your capacity is huge, your network simply just memorizes the training data, noise, and everything, and training error drops to zero, but generalization error explodes. Our goal is to build a model that remembers the past, and it's built a model that generalizes the future. So we're comparing L1 and L2 regularization. So to stop a high capacity model from overfitting, we use regularization. Think of regularization as a penalty fee we charge the network every time its weight gets too large and overly complex. There are two main types are L2 and L1 regularization. Let's start with L2. L2 regularization, also known as weight decay, adds the sum of squared weights to our loss function. It forces the network to distribute its reliance evenly across all inputs, keeping weights values small and smooth. L1, on the other hand, adds the sum of absolute weight values. It acts as a harsh filter, driving less important weights all the way to absolute zero. This creates a sparse model, effectively cutting out unused connections entirely. And you can see here some visuals. L1, also called Lasso, by the way. Now, let's talk about dropout. So, one of the most effective and popular regularization techniques is dropout. So, during training at every single pass, we randomly deactivate a percentage of the neurons, usually around 50%, turning them off completely. So, why would we intentionally break our network? Because it prevents co-adaptation. The neurons can no longer rely on specific neighboring neurons to carry the load. Every single node has to learn useful features independently. It's like training a sports team where random players are benched every play. The remaining players get much stronger and adapt faster. At test time, we turn all neurons back on, but we scale their outputs down so the overall signal strength stays consistent. It's almost like you have a student that everyone's copying of. Well, what if one day we just take that student out of the class so everyone can copy of them and they have to learn for themselves? That's another example. Now, finally, let's talk about stabilizing and speeding up optimization. First, batch normalization. See a diagram right here. So as data passes through deep layers, the distribution of layer activation keeps shifting around, a problem called internal covariate shift. Batch norm fixes this by recentering and rescaling the data for many batches during training, keeping activation stable and letting us use much higher learning rates. Second, when it comes to rolling down that gradient descent loss, like the loss ball that we talked about, previous videos, like standard stochastic gradient descent can get stuck easily. That's why most modern architectures default to the atom optimizer. See right here. Atom combines the best of two worlds. Momentum, which builds up speed in persistent directions like a rolling ball, which adjusts the learning rate for each individual weight based on its past gradients. It's fast, adaptive, and reliable. And that wraps up, our core neural network fundamentals. So we know how to build a network, how to train it, and how to keep it from failing. Now, next up, we'll explore about computer vision and look at how machines process grid data using something called CNNs or convolutional neural networks.